Hello, my name is James Chow. I work with John Sato, Chris Lucero, Doug Lane at NIWIC, which is Naval Information Warfare Center Pacific, and I am here to present our paper evaluating reinforcement learning algorithms for evolving military games. We start with some background. Reinforcement learning has achieved superhuman level of play in multiple games now, including StarCraft 2, Go, chess, shogi, and Atari games. But perhaps most impressively, it came up with novel strategies that pushed human understanding of the game further where it would have otherwise taken perhaps hundreds of years for us to develop given our current understanding of these game strategy and the current meta of the game. However, one issue with reinforcement learning has always been the agent's inability to adapt to changing environments. For example, if you take the AI of AlphaGo and make it play chess without any more training, it wouldn't do well. Or if you change the layout of an Atari game, the agent also wouldn't do so well. This study focuses on training a AlphaZero reinforcement learning AI model on a specific war game, and then testing the robustness of the model to changing environments and rules. Note that this is different from testing the algorithm robustness and generality. Although we did perform some tests on the AlphaZero algorithm generality, and we experienced that the AlphaZero is pretty good at continual learning of new things, but it also is subject to catastrophic forgetting on how to play the first set of rules as it starts to learn the second set of rules for the game. AlphaZero was chosen for this study due to its known generality compared to other reinforcement learning algorithms, as it can be used to master 3 games, including Go, chess, and shogi, and also the degree of success it has had. It came after AlphaGo, which can only play one game, which is Go, and this came before MuZero, which is even more general in terms of the needs to be given of game rules. And MuZero also plays Atari games. AlphaZero is basically a neural network that will learn the states that lead to wins, aka lead to more rewards, using the loss function L here. And the states are traversed through a Monte Carlo tree search algorithm, which will be used for policy improvement. Polynomial upper confidence trees, which is a variation of UCB1, is used to calculate the confidence level of the Q values, where the Q is the expected reward and C is a parameter where you can change to either increase the exploration or decrease it. And then N is the number of times we took a specific action to get to a specific state. Our approach to the problem is to start off with the simplest version of the game that we want to play, and then train the AI agents in that simple game, and then slowly add complexity to the game and observe how the agent performs within the new game. So we will start with complete board symmetry, game objective symmetry, meaning it'll be a zero-sum game where both teams just try to destroy each other and all of their assets. And there will be no changes in the middle of the game as well. We invented a game called Checkers Modern Warfare, which is a war game that is abstracted from other more complicated games. And this will represent our simplest game that we want to start with. Each team will have 3 ships, and the board is an open ocean, meaning every spot on the board is allowed to be moved to. The starting position is shown in the figure here, where they are in opposite corners, and each piece represents a ship. Players will take turns doing one action at a time. You can move one ship, one grid over, or fire at a range of 1 to destroy another ship. In the simplest form of the game, every move is deterministic. Both teams have symmetrical objectives. The board is completely symmetrical. The game is zero-sum. It is sequential turn-based game. And perfect information, meaning each player will see everything happening. The state and action space are discrete. And there is a finite game length. So usually after 50 turns, if one player does not win, we declare it is a draw. And the fire range and life and damage is all 1. We trained our agent using these parameters. We have 200 iterations. Each iteration is 100 episodes. Each episode has 20 Monte Carlo tree search game examples to train the neural network. In a way, the best moves found from the 20 simulations are used to update the policy. There are 40 self-play games after the Monte Carlo tree searches. And the new model is going to have to win 60% of those 40 games against the latest model in order for us to update the model. We use 1 for C, which is the exploration parameter, and this is the least amount of exploration because we found that this shortens the training time a lot and didn't affect the outcome that much. And then the rest are just standard neural network hyperparameters. And we see that after 10 iterations of training, the performance of the agent really starts to converge when we evaluate it pitting against a random agent, as it wins 41 games and loses 8 and draws on 51 games. The reason we pit it against a random agent as opposed to another trained agent or a heuristic agent is that because in the simple game that we created here, the agents actually will eventually just hide from each other forever, since the player who makes the move to go for a kill always will get killed before it. So this could be a flaw in our game design and our method in which we want to start with the very simplest game. which we will take lessons moving forward. Pitting against a random agent here is just a way to show the agent we trained is actually learning how to play the game. The first change we added was adding non-symmetry to the game board itself by adding land spaces where the agent cannot navigate to. The land spaces are shown in this diagram by the black spaces. The trained agent on the old game won 70 games, lost 1, and drew on 29. We think this tells us our model can play well with these new game rules. And the agent is still trying to play the same game. Moves that it would try to perform with the old policy would sometimes not be allowed in the new game, and it would become null moves. But playing in this circumstance, it is still able to play the game fairly well. Will this work with other reinforcement learning algorithms? This is something we would like to test in the future to compare results. However, AlphaZero seems to be able to deal with this change pretty well. The second change is board symmetry halfway through the game. So the game starts with the lands that you see in this graph. Then it becomes open ocean after 25 moves into the game. The agent was still able to win 68 games, lose 4 games, and draw on 28 games, giving a similar performance. Then, with the non-symmetrical board, we added 3 reinforcement ships for both sides at random spots 25 steps into the game. And the agent won 80 games, lost 6 games, and drew on 14 games. Next, still with the non-symmetrical board, we removed any ships at 3 random spots 25 steps into the game, perhaps resembling underwater mines blowing up ships at a certain time. And the agent won 84 games, lost 11 games, and drew on 5 games. Next, with the same board, we add 3 reinforcement ships for both sides at a predefined static spot mid-game, so 25 steps into the game. And the agent won 77 games, lost 2 games, and drew on 21. Finally, with the same board, we removed any ships at 3 static locations 25 steps into the game. And the agent won 83 games, lost 8 games, and drew on 9 games. This shows that the agent performed overall pretty well given the changes that we made shown on this slide. Next, we added some stochasticity. First, we made 20% of the agent's action become no ops. Perhaps this resembles when you move, the rip current of the ocean causes you to stay in the same spot. Or if you fire a weapon, the wind blows it to somewhere else where it misses the target. The model trained on the base game wins a little less at 55 wins, 10 losses, and 35 draws. If we up that to 50% actions becoming no ops, the agent wins even less with more draws now, with 34 wins, 10 losses, and 56 draws. As the agent is now probably more confused since the game is even more different. And if we up it to 80% actions, becoming no ops. Most games now become draws since so many actions that the agent is taking is becoming no ops. So we decided to increase the number of steps before you reach a draw game to 120, and now it wins more and loses about the same and still draws on 53 games. This shows us that the AI model is still trying to play the same game and can still win against the random agent. It just becomes harder to play the game, which we think would be a similar situation for human players. The difference is the human player would learn the new game online, where our agent will not, unless we change the algorithm to continue to train it online. However, it can still perform pretty well in these new game rules. And again, this shows that our model is robust enough to ignore these changes in the game rules. Finally, we added another win condition, which is capture the flag. So now you can win by either killing the other team or moving to a spot on the map first. With this, our agent won 42 games, lost 3, and drew on 55. We then added this new win condition halfway through the game, so at 25 game steps. And the agent won 41 games, lost 4 games, and drew on 55. This performance is pretty good. It has very little losses with slightly more draws, and this might be because it is still winning on the old game condition. So we eliminated the old win condition, and thus now it's completely changing the game objective altogether. We see a similar number of wins with 45, but now a lot more losses at 20. So maybe the agent doesn't know about the new win condition and isn't really preventing the random player from winning by accidentally moving onto the location to capture the flag. So it is still trying to play the old game and can still win. So it is good to see that it is at least not completely thrown off by the new game objective. We then proceed to change the game objective mid-game. So the first half of the game, you have to win by eliminating the other player, and the second half of the game, you can only win by capturing the flag. And the agent had similar results, winning 45, losing 25, and draw on 30. This is some additional work we did after the paper was submitted. So this is not really in the paper, and it's more on transfer learning. This is really testing the algorithm robustness as opposed to the model robustness. So we are training the model on one game and then training it on the second game and then see if it can learn to play both games at a good level using the same model. We have 4 models here. The first one is training it on 18,000 episodes of Gomoku, which is Connect 5 on a Go board. The second one is taking the first model and then training 2,000 episodes on Othello, which is another classic board game. The third model is after we take the second model and train it 7,500 more episodes on Othello, so further enhancing the policy according to the Othello game rules. And then finally, the fourth and last model, we take the third model and then train it 7,000 episodes on Gomoku again. For the results, when we pit the third model against the first model in the game of Gomoku, Model 1 wins 36 games, loses 5, and draws on 9. So the first model is way better than the third model at Gomoku, showing us that after training on a different game, the model forgets how to play the original game. And then we pit Model 2 against Model 3. And this time, Model 2 wins 37 games, loses 7, and draws on 6. Model 3 was trained more on Othello than Model 2, so this shows that more training on a different game leads to more forgetting on the original game. We then pit Model 1 against Model 3 in the game of Othello, and Model 3 wins 48 games and loses 2. So this shows that the model that we trained on Othello eventually learns how to play Othello and beats a model that was never trained on Othello a lot of times. Finally, we pit Model 4 against 3 in Othello, and Model 4 wins only 9 times, and Model 3 wins 41 times. And this again shows that the model, after training on Gomoku, finally, it also forgot how to play Othello. So for conclusion and our learnings, we learned about some of vanilla AlphaZero's limits. This includes the inability to deal with infinite long games, and this is because Monte Carlo tree search is designed to only receive rewards at the end of an episode for AlphaZero. So we need to include a draw condition, or else the tree depth just becomes infinitely long. Second, the AlphaZero algorithm is a self-play algorithm, so meaning one model or agent plays both sides. So the objective of the game has to be symmetrical, and they both have to be trying to achieve the same thing. And then the training process is relatively sample inefficient. We were training everything on between 2 to 4 Tesla GPUs for this experimentation. And for example, when we increased the board size, it made it impossible to train in a reasonable amount of time. And finally, this is a sort of a general machine learning thing, but the board size is directly an input into our neural network. So we can't simply change the board size and train the neural network. So that is one change that we couldn't really deal with. we could try something such as padding the inputs, but it would simply make the training slow down a lot as well. Furthermore, we found that AlphaZero is robust to board symmetry, non-deterministic, so stochastic game rules, mid-game changes, and that we can always train a new game rule towards the policy. However, that, as we've seen, is subject to catastrophic forgetting of the original game rules. We suspect that a lot of the robustness is because it's trying to play a similar game, although it is harder to win, but it can still achieve it since the goal is not that different. Again, we haven't really tested other deep reinforcement learning algorithms in Checkers Modern Warfare, but just from our experiences with training it on different war games, we often see that a change in the game observation space often really affects the behavior, but I think there's more to be looked at there. And finally, one learning is that we discovered that agent behavior, when seeing new complexity or change, is not really one-to-one, meaning it doesn't see a new rule happening and then just add a little bit more strategy to fix that policy and then play it sort of how a human would. But instead, one rule change can change the entirety of agent behavior. For example, if you change the game to do multiple moves per turn as opposed to one, then the agent may no longer need to evade the enemy as the optimal strategy. And it may incentivize the agent to become more aggressive. So perhaps after a change, the agent needs to be retrained as though it is learning a new game altogether. This is sort of something to be aware of when you think about our methodology of starting from the most simple game and using curriculum learning. Because if the game really changes as much as we intend it to, from the very simplest to the most complex, then the curriculums might be contradicting with each other. So just something to be aware of. For future work, we would like to add additional complexity and changes to war games and test how AlphaZero model algorithm handles these changes, such as the one listed here. And then we would like to test how different AI algorithms handles changes compared to how AlphaZero would handle these changes. And then finally, we all work on a program called DARPA Sail-On, which is similar to our goals here. Basically, it is defining novelty and how it comes up in certain situations. And then there is also research on how AI is to deal with this novelty. Thanks for setting up this great conference under these circumstances. Thanks to my colleagues for helping me on this work, and thanks for letting us present our findings.